All right, we are going to be looking at our last and final volume type situation, and this is going to be volumes by cylindrical shells. So sometimes it won't make sense to use the disc or washer method in order to create these volumes of revolution. For example, if we had this function f of x, but you wanted to revolve it this way, then you would have different pieces, and that's okay. Like you could have this nice, pretty cylinder piece if you wanted to, and then break it into this piece, I guess. You'd have washers up here, right? So you could do that if you wanted to, or you could even be like, oh, big R always stays the same, and so I'm going to take it around, and then I'm just going to take out this little piece. Like it's possible to do that, but we don't really like to do that when there are other ways to do so. So another way to do this is to think about revolving a dx piece. Oh, also this would make us have to do it in dy, right? You're going to take a dx piece, and then you're going to revolve it this way. So let's think about this. Your radius is now whatever x value you are at. And then your height is defined by your function value. And then we want to be really careful here though, because if I were to do pi r squared h, then I would be finding the volume on the inside, and that's not really what I want to do here. Because if I do that, then I'm going to be finding this volume plus this volume. Like, I know that's kind of what it felt like we were doing before, but this is going to be like way too much volume if I do it that way. Instead, I want to think about like what shape am I actually finding the volume of? And I want you to think about this like a roll of paper towels. Okay, so if you think about this as like a roll of paper towels where that whole thing has a volume, but when you unroll it, it has a sheet, it has a rectangle, right? Like if you were to pull off this outside layer, you would actually end up getting a rectangular piece. And so one revolution around, one roll of the paper is actually a rectangle. It still has a width of dx. It still has a height of f of x. Okay, but you got to think about what the base would be. The base would be 2 pi r, or 2 pi x in this case. And so that's what's going to make cylindrical shells a little bit different. There's some more pieces here where you find like your little delta x value because you're looking at the change between the two x's. I think you can see in the picture like you're looking at that thickness there, and then we're letting that go to 0 so that way you get that solid piece. And literally think about it as being as thin as a paper towel, like super, super, super thin. So again, that when you're doing a rotation, let's even do like x squared plus a little bit. Okay, and we're revolving this way. So you're going to be creating like a bowl shape because you're taking this and you're going around this way. But if you were to unpeel that one layer, right, you'd get a rectangle. Where here you're going to get this, and it's going to create, again, that little bowl shape there. So all of this math, your delta x piece, is this, your dx, okay? You're going to end up having wherever you are here, that's going to be your x, your delta x. And then your function value is your height. And remember, this length is 2 pi x, which is where this 2 pi is going to come from. So you got to think about when you're finding, I know you're finding the volume and we're talking about almost like a surface area, but it's like adding up all the surface areas of the paper towels over time. So if you were to unroll the whole thing, you'd get the area, paper thin, and you'd get the volume once it's all together. Okay, and again, here's another kind of better visual, a 3D visual of what that's going to look like. All right, so if we're going to be using shell method, then this is going to be our thought here, right? Let delta x get paper thin. Let that sum go to infinity so that your delta x is as small as possible. And you have both the rule and then kind of the Riemann sums to the integral version here. All right, let's look at 1 over x and the x-axis from 1 to 3. And I want to find the solid one revolving around the y-axis. So again, let's talk about why we might not want to do this with disk. If we were to do this with disk and we are trying to figure out, we'd have to have a big R here to here is like a set of big R's, but then your big R changes. So you're going to have to figure out what this here is. It's not terrible, it's 1/3, but I would rather stay away from fractions if we can. And then from 1/3 to 1, and then again, we have to convert everything into dy's. So there's a couple reasons why we just might not want to do all of that. And instead, we'll keep everything in terms of x and use shells. So goodness, that's a mess. Okay, pretend like that looks okay. Okay, so I'm going to still integrate with respect to x. So I'm going to integrate from 1 to 3. So I don't have to worry about there being any weird spacing or anything because this distance to here is still just x. And then my height of each one of those is just my function value. I'm just going to set this up. We won't be integrating here just for the sake of time. So I'm going to integrate from 1 to 3, 2 pi x times f of x dx. Because again, if I were to unravel that piece, this would be 2 pi x in length. This would be f of x with a width of dx. And I would need to add all of those up. All right, let's look at another example. We are looking at 2x minus x squared over the interval from 0 to 2. And again, I want to go around the y-axis. Well, the zeros of this are going to be at 0 and 2. And then it's a parabola that opens down. Now, this is a huge reason why we need shell method. And if you were to do big R and little r here, you're going to run into some issues because you're going to have the exact same function. So this is another one where I'm like, oof, we need another method. Okay, so I'm going to leave this in terms of x. It's going to make like a little bundt cake. All right, so it's going to go round and round. That. Okay, where this is distance x, this is distance f of x. And when I unravel one of those sheets, this is 2 pi x, again, circumference of that circle, f of x with a thickness of dx. So we're going to integrate from 0 to 2. 2 pi x f of x.